Welcome, everybody. Thanks for joining us today. I want to welcome everyone from the CNMI and Guam and all our other attendees. Today is going to be session 9 for our U.S. Territories Wastewater Operating Training Series. We are the Environmental Finance Center network, as many of you guys know. My name's AJ, and I'll be your trainer today. And today we will be talking about preliminary treatment or pre-treatment. Like I said, I am AJ, and I'll be your trainer today. We are joined by Valeria Cortez Mora. She is an intern with the Southwest Environmental Finance Center. She's going to be monitoring the chat, as well as loading up our poll questions and stuff like that. If you guys have any questions, go ahead and type them in, and we'll try to both get to them. Real quick, just a little bit about us. We are the Southwest Environmental Finance Center. That's our part of the Environmental Finance Center network that we mentioned earlier. We are based out of the University of New Mexico School of Engineering, and this training is provided to you guys by funding from the EPA. I'm sure by now many of you guys are familiar with our controls and the Zoom controls. But if anyone needs a little bit of a refresher, you have your little bar that can control your audio, your video, when you want to ask questions, if you want to send reactions and stuff like that. This training and the series overall is designed to be based on the framework from the WPI or the ABC Operator Certification Program that provides testing throughout the country for wastewater operators to certify them that they are qualified to do their job. Our topics typically cover the level 1 and 2 criteria that will be on your exams, and sometimes some higher level topics. We, of course, cannot cover everything on here, but we do our best to give you guys a pretty general overview of all of these topics, and in depth enough where you guys can get some ideas of what's expected of you as an operator and what's expected of you to become certified. As I said, this is a series. This is our remaining schedule for the rest of the year. We are currently here on the topic list, providing training for preliminary treatment or pre-treatment, like we said. And then the next couple weeks, we are going to treat on primary treatment, sedimentation, and then early next month, we'll be training on fixed film media. We have 4 more training sessions for the year, and then we will have begin the training series again next year, early in the year. All of our recordings for these sessions can be found at the website on the top of the screen, our swfc.unm.edu/home/opcert-trainings/. And then the last kind of admin thing is just for a quick reminder for everyone. Make sure if you guys are attending this training as a group, that you go ahead and everyone make sure to sign in that sign-in sheet and provide it to the facilitator so that we can make sure that we get everyone credit and everyone gets those attendance hours for completing the training. So with that, let's get to today's content. And the first thing I want to do is have a little bit of an interactive question. So I'd like everyone to think about this question of what is the goal of pre-treatment at the wastewater treatment plant. I'd like you to think about that question and type in what you think pre-treatment is in the chat. Keep that question in mind, and go ahead and maybe provide some answers, and let me know what you guys think in the chat. We can get a little bit of interaction going early in the morning. I'll give you guys about 30 seconds to a minute, depending on how quickly we get some answers. So the first one is eliminate pollutants from the wastewater stream. Is there anybody else? There we go. To eliminate potential hazards, to protect equipment, good. To remove rags and grit, great. Yeah. So let's go ahead and keep those in mind. Everyone were right there with what I was looking for. Especially to eliminate potential hazards, to protect equipment, and to remove rags and grit. Good job, everyone. So that kind of brings me to our definition of what is pretreatment. So pretreatment is the physical removal of solid material from wastewater influent to protect wastewater treatment plant process equipment. So there's that protecting equipment. There's the removal of pollutants, right? Because solid material is typically going to be pollutants in our wastewater treatment. And this is specifically going to be things like trash, rags, rocks and sand, eggshells. And then, like you guys said in the chat, the goal is to protect downstream equipment. So we remove these things because they can get clogged, they can cause unusual wear and tear on our devices. So we have pretreatment in our plants to go ahead and remove these contaminants from the wastewater so they can't cause damage to our wastewater treatment processes and our wastewater treatment equipment. This is especially true for things like pumps, for mechanical equipment on sedimentation, for mechanical equipment and pumps in our activated sludge, in different other biological processes. We remove debris because it interferes with our lagoon processes, all of the kind of above. So when we are learning about pretreatment, we like to kind of we all like to consider all of our pretreatment processes as the things that are in the headworks. So we want to discuss all the functions that are kind of associated with your headworks when we're talking about pretreatment. And the processes that are typically included in this, this is going to be where our trunk lines and our interceptors merge. So all of the influent wastewater that's coming from your collection system will meet at the headworks. And this is also where we start to assess our wastewater by having flow measurement. This is where our different pretreatment processes come in, screening, grit removal, those processes. And then, like I said, this is where we start to assess things, and that can also include sampling and actually performing analysis on the wastewater to understand the contaminant and pollutant content of that wastewater. This is where we would implement some odor control measures or processes to start removing those odors that build up in the anaerobic conditions of the sewer collection system. We also may have flow equalization, where we make sure to where we ensure that our wastewater flows are consistent throughout the day, and we don't have too low or surges that can interrupt our wastewater treatment, or that we have to make too many adjustments for. And then also flow equalization basins can also act as emergency storage for those wastewater surges. And then the final kind of headwork process that I want to point out is pre-aeration. This step is usually used for processes that suffer from the anaerobic conditions of our collection system. With that, let's go ahead and talk about our first pretreatment, or our first process of the headworks that is part of pretreatment, which we mentioned earlier was our flow measurement. And again, I kind of want to ask a question, not to you guys, but we're going to ask a question to start learning about flow measurement, which is, why do we measure our flow? And like we said, or well, not like we said, but the first thing we have is that flow indicates if processes are operating within their design parameters. So if we have different processes that are designed to accommodate a certain capacity of wastewater, making sure to measure our flow helps us understand if we are exceeding those, if we're well below them, and it can help us explain why things may or may not be running correctly. And then this is where, like I said, it's kind of our first step of our influent assessment to understand kind of the nutrient content, to understand what kind of heavy metals there are. This is kind of building on that to understand if we need to have like future innovations, if we need to adjust our treatment and stuff like that. And then the next question I have is, that we want to answer in this section, is how is flow measured? Typically, our flow is measured in as a flow, which is going to be a volume of water per unit of time. This is typically calculated using a couple of simple equations. So for our channels or our pipes, we usually have our volume, which we calculate based on the area, the cross-sectional area of a channel or pipe multiplied times the length. And then typically we divide that volume for how long it takes a particle or a stick or sort of other measuring device that floats on the surface to travel from one end to the other, so indicating the amount of time it took that volume of water to travel from one point to another. And that will give us our flow. And then the other way we measure our flow is multiplying that cross-sectional area times the velocity of the water or an item moving in that water. Now, we don't necessarily just do the math all the time in our wastewater facilities. Typically, what we use is we use different flow measurement devices. And there are a variety of these depending on the age of your plant and depending on just like the technology available. And the different flow measurement types of devices that you might see are magnetic flow meters. These typically measure the velocity of the wastewater passing the probe and sends a signal between those probes. You may have something like a partial flume and V-notch wares, which are better known or which are known as head area flow meters. They create a mathematical relationship between the depth of the water and how much volume is actually flowing through it. You have rotometers, which work on a constant differential of the pressure created by the flow. You have ultrasonic level meters, which work the same as partial flumes and V-notch weirs, but are a little more, which are more modern techniques of taking your depth and using that to measure your flow. And they're more easily able to interpret that data to a digital system. And then just some quick, tips about operating your flow measurement. We want to make sure that flow meters are placed in easily accessible areas for maintenance, and that they are in a long, straight section of pipe or channel, so they are measuring an accurate representative sample of your wastewater influent. We also want to make sure they are placed in areas where they're not overly confined for safety reasons for that maintenance and for inspections as well. And then another typical thing is that, when you place in those long channels and you're getting representative flow measurements, you should also make sure that when we are calibrating and working on our measurements, that working on the maintenance for these meters, that we do that with the device installed where it is currently measuring. So with that, let's talk about a little more in detail about the different kinds of flow measurement methods and how they work. And we'll also kind of show what they look like. So, like we said, we have our head area methods, which include different types of weirs and flumes. And the way these work, they measure the surface level depth, which is called the rise or the head of the flow in an open channel. And then you have a mathematical relationship to calculate the flow. So that head measurement is used to calculate the flow, and you either take a number of that head, and you might have a chart that indicates the flow, or you can plug it into a formula that you have kind of readily available. A lot of times what this looks like is just little markings on the side of a channel like this, that, maybe, inches apart or a couple centimeters apart. And instead of having depth measurements, they're actually going to say things like gallons per minute, cubic feet per second, those actual flow units. And then, this specific example is an ultrasonic meter. As you can see in the middle of that channel, there's an ultrasonic device. And that's doing the same thing that you would with a head measurement, but it's measuring it with ultrasonic sonar. And then it is sending those depths back to a receiver where it is calculating the GPMs or the flow based on that ultrasonic depth. Then there's those rotometers that we kind of talked about. These are those constant differential devices. So what happens is you have a float that's placed in a clear tapered tube that indicates the flow. This would be either as markings on the tube that indicate the flow, or markings that can be used to plug into a sheet or a conversion form, in the same way that those head measurements are as well. Um, so what happens is these tubes are placed vertically in line with the flow, and the pressure differential increases as it pushes the float higher in the tube. That shows kind of that higher GPM. Now, like we said, it has those markings, and those markings are directly scaled to indicate the flow through the tube. The next one is our velocity meters. This is those things like our magnetic meters, which measure the velocity of the wastewater and passes through signals. We can see an example of this in this picture. You have that kind of differentiated section in the middle of the pipe with a meter on it. What they're doing is they're just isolating that section so they can have signals that go from one end to the other and indicate how fast the water is going through. And then based on that cross-sectional area of the pipe, these type of devices automatically calculate your flow. Then you have kind of a lower tech version of this, which is a propeller meter, where you would actually have a propeller in the wastewater as opposed to electrical probes. And as the wastewater moves, it moves those propellers at a certain velocity, and that velocity is then converted to flow, again, using that cross-sectional area to measure the flow through the line. Now, these type of meters do have a couple associated devices with them. This would be something like the transmitter, which will transmit the data of the velocity. Then you have your receiver, which receives that data. And then you would have a computer program or a device that totalizes that to produce how much flow you're having in the moment. And usually you have SCADA that works along with SCADA or other programs that kind of show the average flow for the day, the week, the month, all those different ones that we kind of have to report, but also that helps us understand how our wastewater treatment plant is running. So these type of meters will look a little something like this. So on the left, we have kind of just an inline meter that shows the flow going out of a pump, which will be the GPMs. And on the right, we have a little bit of an older model, which is producing a analog read and is printing out the different numbers at different times a day. And with this one, you can use to perform totalizer calculations because you have the total number of volume that's used. And then with that piece of paper, you would also have timestamps on it of different times a day, what those flow were. And then you'd be able to take that to calculate, your average flow. But then right under that, as you can see, it says 253 GPMs. That's going to be your instantaneous flow that's showing. So you can kind of have this type of device that kind of shows that long-term averages as well as that instantaneous amount to understand how your wastewater is moving. When we use these devices, it is a good idea, especially for our smaller systems, to be able to totalize those calculations. So in order to do that, like we said, we have our calculations used to measure the average flow for your plant. And these calculations are not over totalized. We just need to know where to get that data from. And that, then we take the flow is calculated by that data, which is going to be your volume difference from one day to the other, or one time period to another, and the amount of time that's passed. And so that looks a little bit like this. So say we have that device that we were showing you before, which has the total volume or running total volume, but then it also will print that out. So you would, in order to calculate how much volume, the amount of volume that you would use for a certain given amount of time, you would take the final volume that you currently have on the meter, or at the time ending that you want to calculate for or reference, and then you would take the volume of the start period, that initial volume, and you subtract that from the final volume to measure the volume that passes through that meter for a given period of time. And then what you do to find the flow is you divide it by that amount of time that actually passes. So these can be pretty simple. If anyone's interested in some, going into more detail about that, you're welcome to reach out to us and we can show you how to kind of perform those calculations. Now, along with understanding what this information means, what data we have, we also need to understand our flow meter maintenance. So our flow meters are sensitive devices that can malfunction easily when they're neglected. So for that reason, flow meters should be inspected and calibrated frequently and preventative maintenance performed when needed. Um, this is to make sure that we are always getting consistent flow meter ratings. This can be to make sure that we're processing our water correctly, we're making corrections as needed, and because this is typically something that needs to be reported as part of our permit requirements. Now, the maintenance is not typically the operator's responsibility, especially at our small plants, and is usually provided by the manufacturer through a service contract. Those sensors and related instruments are sensitive and have device-specific maintenance requirements. So it's usually best to kind of stick to those arrangements unless you have an instrumentation person at the plant. Now, even though it is likely not going to be us as operators who are responsible for calibrating or even maintaining those flow meters, there are a couple of things that we should know about them. So if you do perform maintenance or you're working with anyone performing maintenance on those flow sensors, you want to make sure there's no electric power to the devices to avoid any potential electric shocks. So that's the information that we have about our flow measurement for now. Let's go ahead and break this up with a quick poll question. Valerie, if you wouldn't mind launching the first question. So this question is, Valerie, this is the wastewater safety. Do we have the one on pre-treatment? Oh, there we go. If anyone can't see this, let us know in the chat. So the first question is, which of the following types of flow measurement meters is an example of a constant differential device? Let's go ahead and take about 30 seconds. And then we'll go ahead and reveal the answers to the poll and talk about the answer real quick. All right, I think that's pretty good. I think we got a decent amount of answers. So let's go and end the poll. We'll go ahead and share the results. I'm just going to kind of show the results of the first answer. So which of the following types of flow meter is an example of a constant differential device? So the most common answer was the correct one. That's the rotometer. If you guys remember, the constant differential devices are the ones that work on a pressure difference and will push a float up that clear tube, which is the rotometer meter. Propeller meters are an example of velocity meters, and then the partial flume and V-notch are our head area meters. Thanks for everyone participating in that. So now that we've talked about flow measurement, the next thing that usually comes in line is going to be our pre-treatment screening. So pre-treatment screening is going to typically be a couple of different types of devices. They can be our bar screens. Very similar to that, our bar screens are our bar racks. And these two devices can either have manual cleaning or mechanical automatic cleaning. And then the other part that we want to talk about with pre-treatment screening is screening disposal. We want to talk about commutators, which are different types of screening devices. And then that'll kind of wrap up what we want to cover in our screening section. So the first device I want to talk about are the bar screens. So bar screens are parallel rows of metal rods or flat bars that are placed vertically or inclined in a channel to remove large debris from the inflow flow. This is done to protect our downstream mechanical processes from damage and pumps from clogging due to the screening material. This helps reduce our maintenance costs throughout the rest of the wastewater treatment plant. Uh, Now, for bar screens specifically, these devices are good, for similar devices, when you have rods that are measured between 3/8 to 2 inches apart, that's when it is considered a bar screen. Um, and the way these things work, the flow through those devices is continuous, and the screen removal is continuous as well. This is either done automatically, or they are raked periodically by a manual rake. Now, oftentimes these devices are designed to have an incline of approximately 30 degrees to allow for screenings to be removed easily, especially on our manual screenings. Um, and then once those screenings are removed, they can be washed to introduce those organics back into the flow. You don't want to reduce too many organics or the biological activity in the rest of your system may suffer. And then so once those devices are washed, they can be compacted to reduce volume, and the water content is removed. Um, and once that happens, they are disposed of by either landfilling or incinerating them. Now, to work properly, these devices are typically made of corrosive um, resistant materials such as stainless steel. This helps prevent damage from common sewer gases like hydrogen sulfide, which can become sulfuric acid. As you see on this device right here, this is two parallel bar screens run next to each other, so you can kind of adjust those channels as needed to account for your different flow levels. Now, a little more up close and personal with this kind of bar screen it is considered a bar rack when the spacing is greater than 2 inches. So they are very similar, and they're kind of designed the exact same way as bar screens, but they are designed to remove larger debris because they have wider spacing. As you can see in the picture, they operate the same way. That flow is running from one inlet to the outlet through this channel and through the bar screens. Um, Now, the bar screens are typically used are not typically used in regular treatment processes, and are more often found in kind of bypass channels, which is to help protect some basic screening when you are doing maintenance. And a lot of times these can have a more moderate slope compared to our bar screens of 30 to 45 degrees. So it's easier to move out those heavier materials that may get clogged on here, like large 2x4s, large rocks, that kind of thing. Then the next thing we want to talk about with our bar screens is the bar screen cleaning. So cleaning the screens off is critical to prevent clogging the bar screens. This helps maintain a consistent flow throughout the pre-treatment process, and also to prevent odors that may be generated by those screenings just kind of sitting on your devices. It usually involves removing debris caught on the bar screens using a manual or mechanical rake. Mechanical raking is kind of a simpler task performed with a hand rake, like a hand rake or a hook, which we were kind of pictured here. And then, for our manual screening, the screenings are simply raked up out of the channel and disposed of in a designated trash bin that will be landfilled or incinerated later. Typically, our annual bar screens are found in smaller or older facilities that don't have the volume of debris that necessarily requires an automated system. This type of device does require more frequent attention, some physical labor, and additional safety precautions. So when people are working on them, they don't get hurt. Now, for these devices are not high maintenance in terms of operation. Your initial operation should include frequent visual inspections to determine an optimal frequency for inspecting and raking those bar screens. This schedule should be frequent enough to prevent the process from backing up, but not so tedious that operators are wasting all of their time just inspecting the small changes or raking inconsequential volumes of screenings. Then also with cleaning your bar screen, there are also mechanical raking systems that rake and transfer screens to a disposal bin, a conveyor belt, a channel, or other type of conveyance mechanism using a mechanical device attached to the bar screen frame, which is what in our next picture that kind of looks like. So we're going to go into a little more about mechanical screening. We'll give it a whole slide because they're a little more complicated and they kind of need more information about them. So these types of bar screens can be the same size as manual bar screens or much larger in large flow plants to account for the higher volume of screenings that need to be removed. Large mechanical rakes allow for the bar screens to still be cleaned properly and prevent clogs, odors, and maintain flow, like we mentioned, for our manual bar screens, but in ways that operators would not be able to because of the larger volume for larger flow plants. This type of bar screen consists of the screen itself to trap the debris, a frame to support the bars and connect the rake and drive mechanism, the rake itself to scrape debris off the bars, the drive mechanism, which moves the rake and is usually made up of a motor, gears, and chains, the track to direct the rake along the screen, the discharge chute to transfer screenings, the control systems to automate operation and execute the time schedule, and then finally monitoring sensors to detect water level changes or debris buildup to trigger cleaning for systems that run on that level differential. Now, systems that run off a level differential automatically trigger the raking process when the effluent side of the screenings experience a determined head loss from the the influent. So the influent side will have a higher depth than the effluent side of the bar screen, which is called head loss. Now, I say it's being a certain amount because it's going to depend what that level differential is. It's going to depend from the device to device. But this is important, and this triggers screenings because if there's enough screenings on the screen, it will cause the flow to be partially obstructed through the screen, which results in the influent being higher than the effluent side of the bar screen. Now, these types of bar screens can also usually have a timed program that acts as a backup to make sure screenings are removed no matter what if the level trigger is not removing screenings properly. These ones also have the same type of conveyor mechanisms, either a belt or a chute that may have some reuse water that comes through it. But those conveyance mechanisms operate continuously to collect and transfer all the screenings or are triggered when an actual screening is triggered as well to minimize energy use. This type of simultaneous sequence is sometimes a channel that, like I said, uses reuse water to wash the screenings down a channel to a washer compactor, which is a good example of reusing the resources created from your wastewater treatment plant. Now, because screenings have a high water content of 80%, it's important to kind of remove some of that water to protect your transfer devices and also to make them easier to handle later in the process when you're disposing of them. This is what kind of some of those automatic mechanisms might look like. As you can see, this screen is moving continuously up, and it's going to drop those screenings onto a dumpster. So we've discussed operation a little bit, but real quick, I want to talk about some of the basic operational recommendations for using bar screens. So these are still simple devices, but like we mentioned, they do require frequent attention. And once you've identified an optimal screening schedule, it's a good idea to put that in writing somewhere, such as a standard operating procedure or a checklist. or include it in the current operator checklist that remind operators of their current daily tasks needed to run the plant. It's also a good idea to track the screenings removed to determine if operational adjustments are necessary, or it is even possible that if you're getting too many screenings, you may need to perform some outreach to the community to kind of let them know about the pros and cons of, or not the pros and cons, but basically the impact of putting things that should not go down the drain down the drain. And then also as part of your rounds, you want to make sure to verify your set points for the automatic screening process, or for the automatic screening, what you would call it, I guess it's a process, but it's more like a cycle for those automatic screening cycles, and make adjustments as needed if it's cycling too often or too little. If it's cycling too often, you're going to see not many screenings come up when it does screen. Or if you're doing it too little, you're going to see a buildup that could be damaging or inhibiting that transfer process. What the Sac State Guide kind of recommends is kind of starting out as 3 inches for a level differential, and adjusting as needings. So if the screenings removed are minimal, it may help your plant energy and resource efficiency to reduce that raking program. Or if there are excessive solids being pulled during that cycle that threaten to clog the screen transfer process, or just excessive solids in general, it may be helpful to increase the program frequency of raking and transfer. Now, for turning on these machines for basic startup, typically what you do is you turn on the bar screen, you open the outlet, then you open the inlet. And then for our shutoff, you basically do that process in reverse, whereas you close the inlet, close the outlet, turn off the bar screen after running it a couple times to make sure everything that was in there is kind of cleared, and then spraying off the unit. Operators want to make sure that the channels are not overwhelmed by utilizing extra channels during storm or maintenance surges, and be aware that when these types of events could be occurring. Now, during operation, it's also a good idea to frequently wash the screen. Your screen transfer devices, such as your conveyor belts. Those belts can accumulate slime and buildup that can make them stick or become too heavy, which can interrupt your operation. Then finally, it's a good idea to periodically check for debris that cannot be removed. This is on the bar screen itself and conveyor device. We already, as wastewater operators, we already know that anything can come down the pipe in our sewer lines, and we see everything in our line of work, from things like 2x4s, barbed wire, etc. And those get stuck in the bar screen and can trap extra material, weighing down our conveyor devices or clogging them. So that's another thing that during our rounds, we want to make sure to keep an eye out for and remove promptly. And when we do that, we want to make sure to turn off those bar screens and lock them and tag them out. Kind of talking about that same line of thinking, we'll go ahead and talk about our bar screen hazards. Now, by far the biggest concern with working around bar screens is slipping or falling into the open channels or tank, especially in our large scale plants that have channels that cannot easily just kind of stepped out at. So large plants often have very deep influent channels that operators will die in if they fall in, or from the fall or from drowning. So for this reason, it's important to keep those surface area cleans around our channel. We want to keep them covered if possible, and only open them when necessary. It's a good idea to have guardrails or safety gates installed, if possible, to protect your workers during cleanings and inspections. During those inspections, you want to make sure those devices are installed correctly and are anchored if they're permanent. Then another thing to think about during this is you want to operate, or when you're going into pre-treatment facilities and when you're inspecting them, you want to make sure that you're working with a partner and using a radio check-in, check-out practice. And then also sewer gases like our hydrogen sulfide, like we mentioned, can be present in our pre-treatment and headworks. And so you want to make sure that if you're in an enclosed facility, you want to make sure to use a gas monitor to measure any of that and identify if you have any hazards like that in your process area. I already mentioned if you're working on these devices to make sure to lock them and tag them out so there's no electricity going through them, and they can't accidentally trigger and crush somebody or pull someone in somewhere where they shouldn't, that kind of thing. The last hazard that we want to mention for our bar screens is kind of our physical strain. When you're raking these, you're physically exerting yourself. You can pull muscles. You can hurt yourself. You want to make sure that you're not pulling or moving any more screenings than your body can physically handle. Of course, you want to use your PPE. Pre-screening is typically where we have a lot of our more dangerous things, like you can have needles, you can have sharp objects in there. So you make sure that you have your proper PE to not get kind of stuck with those kind of things and then be exposed to more pathogens. Kind of remember our screenings are dangerous. And because they are hazardous and dangerous, we want to make sure that we dispose of them correctly. And then another reason is because they have odors. Disposal should not, when you dispose of these, they should not affect your surface or groundwater supplies. And these are typically landfilled, so you'd want to coordinate with your local regulatory agencies to avoid compliance issues. This may require something like a paint test to make sure that your screenings are not seeping contaminated liquids into the groundwater. And then when you're disposing, to make sure that you are accounting for how many screenings are coming through and how many screenings you need to account for in the future, you want to make sure to track those disposal volumes for future planning. And I'm just going to show you a couple quick equations about kind of that screening. We're not going to go into too much in the math about it, but something you want to understand is, you have your screenings removed. That'll typically be in gallons or cubic feet per day, so a volume per day. You may equate this to how many millions of gallons of flow you treat. And kind of based on that, you can use a conversion factor to figure out how many screenings you are producing a day, a month, a year, and this can help you determine your filling rate. Your filling rate will be essentially if you take your landfill pit, and it's going to give you a rate for how long you're filling it, and kind of based on the size of that pit, which would typically be a volume as well, you can divide that pit volume by your filling rate to determine how long it's going to take you and how much capacity of time you have for your current landfill site. There are some other ways of dealing with our rags and our screenings. A lot of times you have something called a shredder or a grinder. An example of this is our communitors, which are solids grinders. These tend to shred rags and cuttable debris, while also grinding up some of our softer grit. So what typically happens is that debris will settle. There is some biodegradation of those shredded debris, and they're able to be treated that way. A problem with this is that those rags and debris can tangle in downstream equipment because they're not completely removed. So a lot of times you kind of see these in older systems. But maintenance and safety practices are similar to our bar screens, being careful around the surface and making sure that you're not having additional electrical hazards. Then the last type of screening is going to be those what we call our rotary screens. We've been seeing kind of an emergence of this in our kind of small to medium-sized plants. What these do is you're introducing wastewater through them, and they spin fast to dry those or to clear out the organics and liquids from the rags. Then you can spray these down, or they have an automatic rinse cycle to pull those rags off of the rotors to be collected and disposed of. And we do have another poll question. It was separated. So we have one more poll, or we have a second poll question. Valerie, if you wouldn't mind launching that. So this poll question is, screen devices with bar spacing of 3/8 to 2 inches are considered what type of screening devices? So if you'll remember from one of our first slides, we talked about a couple parameters that indicate what is defined as different types of devices. So that's what this is from. And the options are a bar screen, a grinder, a grit channel, or a bar rack. I'll give everybody about 15 more seconds to answer this, and we'll talk about it. All right, we got a couple answers, so I'm going to go ahead and end the poll. And I'll go ahead and share the results. So most of us answered correctly, and that's bar screens. That's what we mentioned, that 3/8 to 2 inches identifies it as a bar screen. Grinders are more in charge of shredding our debris than collecting it. Grit channels are for grit. And then our bar rack is when you have a larger than 2-inch gap in the bars. So good job, everyone. So with that, we'll go and talk about our next section, which is going to be our grit removal. So grit is identified as that heavy particulate matter found in wastewater. This can be sand, eggshells, bone fragments, seed, coffee grounds. These are especially important to remove from our wastewater because they damage our pumps and other equipment, but mostly our pumps. They are really good at deteriorating things like impellers. And then they also fill our digesters, which decreases their capacity and our ability to produce biogas. There are a couple of ways for removing grit. The first is going to be our grit channels. These operate by removing grit that settles to the bottom of the channel. They slow down the flow, either by having like kind of like a long channel and then controlling how much flow is in there and making sure that that flow is at settling velocity. So the optimal settling velocity is between 0.7 and 1.4 feet per second. 1 feet per second is considered the ideal velocity where flow will settle out the easiest. The particles that settle out are typically 0.2 millimeters, and they have an average settling rate of 0.75 feet per second. What tends to happen is the heavy grit settles to the bottom of the reactor at that settling velocity, and our lighter organics are allowed to stay floating in the wastewater and can be used later on for our biological processes. Now, grit disposal and safety practices, again, are similar to bar screens. We want to do some landfilling. We want to make sure our surfaces are clean. We want to make sure we're safe around our mechanical devices. So our grit channel operation is pretty simple. It's accomplished typically by installing a multi-channel chamber or a proportional weir. The velocity can be calculated by placing a stick on the flow surface level or having our surface meter devices. Our flow measurement devices. Again, you can use that flow measurement if you don't have access to a flow measure device, measuring your velocity and comparing it to your cross-sectional area. It's good to have an idea of the flow during the low, average, and high flows, and then you can adjust your channel as needed to make sure you're still near that 1 feet per second. So once you make sure that your flow is running at the correct speed and you have the correct volume going for your flow, then you want to account for that grit removal. This is basically done using a long scoop shovel or a built-in vacuum mechanism where you kind of just scoop it out and dispose of it in a dumpster or something similar where you know that you will relay it to a landfill. As part of the operation, you want to make sure to inspect the grit to make sure there's not excessive organics such as biofilm and stuff like that accumulates on the grit, which should instead be being treated biologically. Because you can decrease the efficiency of your plant if you don't have enough biologicals going into your activated sludge, and instead they're being landfilled. Another version of this is an area grit chamber. Now, these are still typically long serpentines or channels, but instead of just relying simply on that time and that velocity, aeration is added to the chamber. Now, aeration decreases the specific gravity of the flow. So water and air together have a lower specific gravity, which means that those grits settle easier. Typically, you're pumping DO into these through some diffusers. Then you also have a pump system that removes the grit as it is rolled or guided towards kind of a channel at a lower level of the grit channel. One added example or added benefit of this type of flow is that it kind of keeps that wastewater fresh, which will contribute to the effectiveness of your activated sludge processes. There's also our grit separators, which uses a series of stacked discs. These discs, as the flow comes in, creates a cyclone. The cyclone separates your liquids from your solids. Your solids are guided down to a chute where they can be pumped out, washed and cleaned. And then your water flows out the top of these channels due to that vortex, which creates an effective settling mechanism. These are more of an emergency technology, but they have been shown to be very effective at large scale plants. And we'll probably be seeing more of these in the future. Now for operation, it's kind of hard to directly view these devices. And you're more of kind of trying to monitor your grit and downstream equipment to make sure they are working effectively. Now, with all our grit, we want to make sure that we wash off those excessive organics, like we mentioned. They can be odorous, and then they also interfere with, if our organics are stuck to our grit, it interferes with our biological processes. These processes are sometimes referred to as classifiers. And then just like those cyclone separators, they work kind of on the same principle of the vortex, where it creates a vortex, our solids are pushed to the bottom, and our water flows out the top. Similar to our rag disposal, we want to make sure to dispose of our grit in a landfill. We can use the same kind of math of our average grit volume removed to estimate the time to fill up a landfill pit. But then one difference is you want to make sure that you place 6 inches of soil on top. That helps prevent vermin organisms from getting into the grit, and also prevents odors. And then again, you want to work with your regulatory agencies to make sure you're in compliance, and that you're, the regulatory agencies, if they have specific disposal practices. Again, these safety practices are pretty common for all types of pre-treatment. You want to avoid slips and falls. You want to keep your surfaces clean. You want to make sure to hose down the accumulated material, and then also install these safety precautions and make sure to use standard electrical safety procedures. And then also make sure to use your PPE. Now, in the spirit of time, we're going to go ahead and skip this poll question. But the poll question was, what is the ideal flow velocity of a grit channel? And just as a reminder, that was 1 feet per second. So real quick, we'll talk about kind of influence sampling. As I mentioned, our pre-treatment and our headworks is a good place to get an idea of the quality of our wastewater that's coming in. It can help us detect pollution events. It can help us optimize our treatment processes. It can help create support for design upgrades if you're getting influent that your treatment process is just not able to handle. Now, a lot of times these types of samples can be either composite or grab. Here is a grab sample, or here's a here is a composite sampler that's going to pull increments throughout the day of your wastewater, so you can kind of get an idea of the average TSS, your nutrient levels, BOD, stuff like that. When performing sampling, you want to make sure to identify the analytes you're looking for, either based on your treatment process or based on your permit, and make sure that you identify the correct sampling methods for that influence. With any sampling, you want to make sure you use clean and proper equipment, the correct preservation methods, that you are using clean bottles that are labeled correctly, that you avoid cross-contamination, and that you follow a set schedule to make sure that you are getting everything you need from these samples. And then, of course, documentation should always be included to make sure that you can identify later where they came from and if there's any process or operational reasons for why samples are the way they are. And then, of course, respond to your results accordingly and make adjustments as needed. Our next section is going to be odor control. So odors are caused by the anaerobic decomposition of organics. This usually leads to sulfur, hydrogen sulfide, like we mentioned, which is also toxic, ammonia, which can be toxic, and then all the volatile organic compounds, such as mercaps, which create gross, nasty odors. Now, odors can be controlled from the liquid. They can be controlled in the gas phase when there are already odors, or with solid infrastructure. One example of this kind of thing is, they have these biological filters, which are controlling it at the gas phase, and you're actually using similar bacteria they have in wastewater to treat and break down organics. You can use natural bacteria that occurs in soils to pump those air through these filters, and then you have microbiological activity, which breaks them down and consumes them. Now, for small systems, you usually want to have portable hydrogen sulfide meter if you're working in enclosed areas. You want to make sure to implement regular cleaning schedules, which cleans out your biologicals that will be decomposed. You want to use well-vented infrastructure, open whenever you can, and low-maintenance technologies that are less likely to have parts that are filled with organics. And then also you want to make sure you are maintaining adequate aeration in your activated sludge processes if you need to also account for those odors. So this is just a couple examples of larger applications of how to control odors. For that liquid phase, you can neutralize odor-causing chemicals through things like hydrogen peroxide, ozone, and chlorine dioxide, or by aerating the wastewater, like we mentioned. That tends to freshen up your wastewater and get rid of the odors. And then for that vapor phase, like we already showed, we have that biofiltration. You can use activated carbon absorption. You can use air scrubbers like the one pictured to the left. And then you can also use ozonation to deteriorate those odor-causing chemicals. In our last section, real quick, I know we're a couple minutes over, but we'll wrap this up kind of quickly, is flow equalization and emergency storage. So a lot of times to account for flow surges, you may have a tank or a basin that is used to store and manage that wastewater flow. So this is an example of a large storage tank that's not currently in use because this plant did not receive a surge flow at this time, and they're running the rest of their flow through their SBR plant. Now this is available to handle any surges and then release into the treatment process at a steady controlled rate. This can help account for flow fluctuations. It helps mitigate if your plant goes down in a storm event or electrical issues. It can give you hopefully enough time to get your plant up and running again while you adjust, while you are able to collect some water and store it for emergency. Real quick, just a couple standard specifics of our flow equalization. These tanks should be designed to manage your peak flows, typically about 4 to 8 hours of that peak flow. There should be mixing and aeration present so that water does not go stagnant and septic. You want to make sure that this is installed before your biological treatment train, so you're not overwhelming your biological treatment train and leaving wastewater in there too long. This can also act as your primary sedimentation stage, where you're removing your initial settable organics. And then also you can have pumping that can be manual timed or have programmable logic based on a variety of your flow coming in, the flow that needs to be treated, that kind of thing. Finally, like I said, these typically have pre-aeration, which helps freshen up your wastewater. It helps kind of initiate your aerobic activity for your activated slow plants. increases your overall treatment efficiency by removing nutrients from the start. And then again, it helps reduce those odors. With that, that kind of wraps up all of our content. Are there any questions? You guys can type them in, or you guys can just ask them out loud, whatever works easiest for you. I'll give you guys a couple minutes to think of anything. While we wait to think of our questions, I'm going to go ahead and put our contact information. So this is the our Southwest Environmental Finance Center email. If you guys want to contact me directly as well, my email is ajbarney1@unm.edu. I'll go and put that in the chat. Feel free to reach out to me if you have any operation questions or anything like that. I don't see any questions coming through the chat. If you are typing, do you want to just raise your hand or turn on your mic and ask the question? Give me about 10 seconds. If not, we'll go ahead and sign off for the day. Again, if you have any, if you did want to ask the question in the open forum here, you can feel free to reach out to us directly. I'd be happy to help with you. With that, I want to thank everyone for joining us today. I hope you have a great day. We really appreciate the support and coming to our webinars. Have a great day, everyone.